Right.
I should know there's a thing out. Yeah, they're buddies. I don't have.
Oh, really?
You can like. Yeah. I mean, unless. It's like social.
Yeah, because it's
Just fine.
Did you see the video? I was like, yeah, it up with this random guy. Just like, watching me. Oh my god. Oh yeah, you feel really cool. Then you watch the video back and you're like, oh, you're like, really that's not what I feel like it's like, you feel like it's a community where it's like 2 seconds. Yeah, or you're like, yeah, like cut back, and then it's like maybe up in the face. It's
back when you have to set one start. That's totally what it was. That's
it's cool.
Yeah.
Thank you for doing that. I was like, I'm sitting here at my boarding. Yeah, it burns yesterday, and he also was you would be this bird. No, I heard it. Yeah. Yeah. And did it feel
Yeah.
she was like, and then
Yesterday,
it's
I was watching.
it's just it was so like I think it would I think it was that had more lights.
Good to see.
Oh,
I can think I read it. And like,
That's okay.
yeah,
what is that?
So do you want to move your
I
slide?
feel like it's like stronger, but I don't know. It's probably like gelatin. No, I think it's like super healthy puree. I think it's stronger. Like there's probably some added sugar, maybe like a preservative or something. And then I don't know on the pages. Yeah. Okay, but there's
You know, not just a second, but it's the second.
like
At least.
If you like, I tried to use like the Oh yeah, okay, but the third one is banana puree. Yeah, they're not labeled as vegan, which is.
Great. Hi guys, welcome to this afternoon. We're going to talk about turbulence. Yay. All right. So I would like to start my presentations with etymology because I like etymology. So we have 2 different regimes of flow, laminar versus turbulent flow. The root word for laminar comes from the Latin lamina, which means sheets or thin plates that are stacked on top of each other. On the flip side, we have the word turbulent, which also comes from Latin. That means stormy or unruly. And it's actually, beyond that, it comes from this word that means like this in a disordered crowd. Like if you imagine a group of people pushing and shoving, that is what turbulence is, which honestly is, as we will see, is not a terrible interpretation for what these things mean. And we also have a pretty good idea intuitively of what it means for something to be laminar. So here I have a Wayfair screenshot of a beautiful water feature. that is mostly laminar flow, and we do see that it does in fact come out kind of like a thin sheet of laminar. And then on the other hand, we have turbulence in a plane, and yeah, makes the crowds disordered. So great. So the outline for this is we are just going to first start with reviewing laminar flows, and then we're going to do some math. After we talk about laminar flows, we'll finally define turbulence and discuss how we would approach quantifying such things or trying to do math with it. Okay, so like I said, to understand turbulence, we need to first start somewhere else, laminar flow. Shashtin this morning called herself an armchair philosopher. So continuing along, oh God. Sharing. Great. So continuing along that strain, Jacques Derrida talked about this idea of différance, which is that meaning is derived not from a definition of what it is, but rather what it is not. So really the best way to define turbulence is to just say it is not laminar. So then what is laminar? This top one is an example of such a flow. It is steady in time, and all of the flow lines are incredibly well organized and parallel to each other. Then on the converse, turbulent would be when something that is not steady, and all of the flow lines are kind of running into each other, acting like a disordered crowd, bumping into each other. So the wonderful thing about laminar flow, though, is that because of how well organized and predictable these streamlines are, we can actually obtain an exact solution to the Navier-Stokes equations. In general, that is impossible because of the nonlinear convection term. If you do find a solution for that version of Navier-Stokes, you get to win $1 million. But we will not be doing that. Instead, we're going to start with laminar flow. Okay, cool. So here is our setup. Say we have two infinitely long plates in the z direction, and we have flow that is going in between the two plates. This is 0, this is h. Those are our coordinate systems. The question that we want to know is, what is u? So yeah, let's go for it. All right. Here's the setup. So we are saying that our flow is fully developed, which means actually I'm not going to talk about it yet. We'll talk about it later. It's fully developed. The plates are infinitely big in the z direction, which means that for all intents and purposes, we can ignore z as a component altogether. There's not going to be acceleration in that direction, and we can set our inertial reference frame such that W is 0. But that's okay. There we have a no slip condition along either plates. So that layer of water has to be moving at the same velocity as the plates. And finally, we have, and then we have no flow through, obviously can't go through a solid wall, and then continuity. So with all of that together in mind, let us go through the math. All right, does everyone understand the problem setup? I mean, most of this is likely review. I'm going to turn them off.
There's no power button.
Hot one? Oh. Nope. Yeah. Aha, cool. Great. All right. So, because we are inside of an enclosed area, there is no free surface. We are also saying that our density is constant. So as a result, we can actually ignore gravity in this set of equations as well, because there is no P prime. and there is no up and down of the water column. And similarly, there is no Coriolis term because we're basically not spinning in our system. So that kind of leaves only these terms in our momentum equations. So one by one, let's cross them out. What can we start by crossing out? Okay, so I did say the flow is steady. What's that mean?
ET is not.
Amazing. What about this one? Yeah, it's the same. Great. We also said that the flow is fully developed, which means that as you go along the stream, the flow is not changing. It looks like a fully set up system. It's kind of, I call it like a slip and slide. It's not the part where you jump off, and it's not the part where you splash. It's the part where you're in the middle at the bottom. So what that means is any gradients in the along stream direction also can just go away. So, okay, I'm just gonna do it. So, boop, boop. Amazing. Great. Third, we have that our flow is laminar and all of these streamlines are parallel. So that means that B should be, because U is not changing in the along stream, V should also not be changing. So we can also see that from continuity, which is du dx plus dv dy, that is 0. So if du dx is 0, dy is 0. The parallel lines are kind of a consequence of that. Great. And because we know what V is, like here along the bottom plate, what is V? It is 0. And if dv dy is 0, and we know one place where V is 0, that means that V has to be 0 everywhere. Excellent. We have more terms that we can cross out. So what are we left with? Right, if we take out everything else, the only thing we have left is in the x direction. We have 0 is equal to the pressure gradient term plus the viscosity term. I know that in general, nu is kinematic viscosity, whereas mu, which is equal to rho times this kinematic velocity, that is the dynamic viscosity, the absolute viscosity. People kind of play fast and loose with terminology there. Okay. Great, and then in the y direction, the only term we have left is the pressure gradient. All right, what does this tell us? Well, starting with the y momentum, we see that there is no up-down, P has no y dependency. So that means that back to our x momentum equation, in here, this dp dx term, that has to be a function of y. And then similarly, practicing for the math workshop. Similarly, because we know that du dx is 0, U has no x dependence. So this term, what? Hang on. Sorry, this has to be a function of x, apologies. And this has to be a function of y. So then that means for this equality to hold for all values of x and y, both of these terms have to be constants. Great. All right, so we know that it's a constant. So this is our equation, and this is equal to some constant. Here we kind of decided to call this mu instead. And all we have to do from here is integrate twice. I'm going to skip the details of all of that. You guys already know how to integrate something by twice. But that gives us that u of y is equal to 1 over 2 mu dp dx. Now this is no longer a partial, it's a full differential. Plus y squared plus dy plus 8. Great. So what is this? This is a quadratic. And that fits with most ideas of, like, if you picture what a profile inside of a pipe would look like, it's pretty quadratic shaped. So great, we know we're on the right track. Then we will use the boundary conditions to solve for a and b. We know that u at y equals 0 is equal to 0 because bottom plate is not moving. So that means that a has not to 0. And then we know that u of y at the top plate is equal to this capital U. That is, did I even mention the top plate is moving? Yes, the top plate is also moving. And it is moving at a velocity of u. So from that, we can solve for b, which is something, which is capital U over h minus h over 2u. So when you put all of that together, you get a full exact solution for u, that u of y is equal to 1 over 2 mu dp dx, and then y times h minus 1. Oh, and then plus u over h. Oh, cool. Yeah, great. Also, I just want to point out the role of the viscosity term here. It is kind of, if you ignore this part, it is relating the u profile to this dp dx term. And that, so it's almost like the thing that controls how much the velocity responds to this dp dx. And that is viscosity. Great. Any questions? Not doing that well. Yes.
I was confused on why u is only a function of y.
Yeah. So we know that u is not a function of x. That's why. That's it.
Oh, okay.
It's either 0 or it's a constant, or it is only a function.
But it can't be u of x and y? Because that would still hold true, right? Because that wouldn't make it go to 0.
Well, we know that du dx is 0.
Oh, okay.
it
So then
has
therefore
no
it has to do that stuff. Okay.
Good question. Yes?
We always find the integral solutions to limit the numbers. Is that like a definition?
I don't think you can always do it. I'm sure you can come up with a weird geometry where there is no like exact solution. I don't want to say something absolute. Um, but in general, the answer to that question is usually no. Yeah. Okay. Anyone else? You look super concerned.
I think I'm trying to follow the step where you went from 0 equals -1 over rho, p dx, blah, 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 to the top line and the middle row, middle column. Yeah. Maybe I just haven't done algebra in a moment.
It is just an idea of if you have two things that are equal to each other.
Yeah.
So if this has to be a function of
And they're a
x
function of different.
and it's equal to a different function of y, then that means for that to be true for every single value of x and y, that has to be a constant.
Okay, I'm totally there. I have one more follow-up.
Great.
I think that here you are saying that dp dx is not 0. Is that true?
I am saying that dp dx is not 0. Yikes. Yeah. Okay. I am saying that dp has no y dependence, so dp dx has to be a function of x. It's not 0. Okay, we're all good? The point of all of this is to say that because of the orderliness of our streamlines and how simple this flow is, we were able to obtain an exact solution that makes sense and makes us really happy. Awesome. Okay, with this can finally come down. Yikes. Oof. Awesome. Yeah, this is just kind of a summary of what we were talking about. It's on the drive. You can go and look at it later. I get to the next slide.
Sorry, I think that you're sharing presenter view.
I am sharing presenter view. That's great.
Is that a share screen too?
Now it looks like I am sharing the right one. Okay, let's move on. All right. Cool. So this is the solution that we just got. If dp dx is 0, then that first term goes away, and the only thing we have left is that u over h times y term. So this becomes a linear profile. Similarly, if that second term goes away, then this is purely a quadratic, and then everything else is some combination thereof. All right. So then what about more realistic flows? This is NASA's perpetual ocean. I'm sure you've seen this slide a billion times. I really like it. And you can see all of the complex patterns that are there in the ocean on the normal day-to-day. Some parts of it look laminar, other parts of it look turbulent. And in fact, most realistic flows is going to be some combination of the two. So how would we try to describe this kind of behavior? All right, let's start with turbulence. So we just went over laminar flows, and we said that turbulence is just something that is not laminar. So we can describe some properties of this turbulence. The first one is it's not, we said laminar flow is steady, or our earlier example of laminar flow is steady. In general, turbulent flow is not. There is a lot of fluctuations. Also, it is nonlinear, which means that a change in the input can produce a disproportionately large effect on the output. One example is this double pendulum. You can see that a very, very small change in the initial condition would lead to a very wide array of possible behaviors. Okay, it usually has a bunch of little whirls, little eddies. So there is a vorticity field inside of turbulent flows. This is an example of a Kelvin-Helmholtz cloud. You can kind of see the little eddies beginning to develop there in between the two layers. And finally, turbulence is dissipated, and it has the effect of making diffusion happen. And earlier this morning, Shasta went over dissipation versus diffusivity. Great. So this is kind of the best way we have of defining turbulence. It's just to describe these things. There is not one singular definition that would work for everything. But we don't like that. We're scientists. We want to quantify things. So how do we quantify turbulence? These are three different types of flows. I am sure you intuitively all have an idea of which one would be more turbulent, which in general, and what kind of flows are more laminar. Why don't we throw out some possible things that we think might affect how turbulent something is? Viscosity. Oh my God. What is viscosity? Okay. Anything else?
Velocity.
Velocity. It's almost as if you guys have already seen this. Yes. And then finally, what is the last one? Yeah, some sort of length scale. So what if I increase the viscosity? How does that affect turbulence? Does that usually make it more or less?
Less.
That's great. Amazing. And whatever you like then. Yeah, it's kind of hard to say. But in this case, we're going to put it on top. So when you put all of this together, you get the Reynolds number. In general, the Reynolds number is the proportion, is the ratio between the inertial forces and the viscous force. If viscosity is stronger, things are less turbulent. If inertia is stronger, things usually tend to be more turbulent. This form uses this kinematic viscosity, so you may have seen this written differently. It could also be equal to rho UL over mu. It makes sense. These two just kind of differ by a factor of rho. So just watch out for which one is occurring in a particular equation. Okay. So
I have a quick question, sorry.
yes.
Is there, I've never thought about this before, but is there a Reynolds component? Is it a vector And if you're looking at three-dimensional space for the Reynolds number from,
So this is non-dimensional.
okay.
It is not.
But you,
Or
but like, if you have like a U, V, and W,
is it turbulent in one direction and not the other? It could be, right?
I'm gonna talk about that on Friday.
Oh, Charlotte's gonna talk about that on Friday. I'm excited to find out.
I'm not gonna tell you, yeah. Come to Friday's lecture.
Great. Excellent question. All right. So why do we call it Reynolds number? Shashton kind of earlier this morning already talked about the Reynolds experiment. So here we are going to just watch this video. Thanks. It's my mouse. This video I will play, please. Yes. Okay, cool. So this is a tube of water, probably, with a dye. And the velocity of the water is increasing over time. So when that happens, that Reynolds number increases. So first it was flat. Now we're kind of seeing this like wavy, sinuous pattern. And if we are to increase it even more, eventually all hell breaks loose and we just have a turbulent crowd once again. So even from this video, it kind of, there is this transitional period between laminar and turbulent. Let's go to in general, as a rule of thumb, laminar flow tends to be when the Reynolds number is about 2000 or less. Although that is not true for all geometries. Earlier in that video, we actually saw it become turbulent way less than that. So if the spout is not smooth or all of these, if you're not very careful, you wind up affecting the geometry of the setup and the transitional Reynolds number is different. It can be less. Reynolds in his paper also mentioned that when he is very, very careful, you can get all the way up to about 10,000 without the flow becoming turbulent. So this is a rule of thumb, but it is definitely not prescriptive. Right. And then in between, when the flow is fully turbulent and fully laminar, there is a transitional zone. Most flows are usually somewhere near that. Okay, cool. I love this photo. The original Reynolds paper is really fun. Like it's one of those old late 1800s papers where it's very first person narrative. And he calls his assistant like Mr. Taylor or something, which is very nice for him to even name it, like your PI. The name. Anyway. Yeah. Yes.
Do you know how, in the context of this paper, the laminar, the transition, and turbulent zones were identified?
Yeah, okay. I'm so glad you asked. I didn't put this in. So what he thought is that you would just have there's a critical velocity. So that was like his goal. He was like, I'm going to look for this critical velocity. And basically he confirmed that yes, there exists some velocity after which turbulent flow happens. And then he would vary the input like size of the pipe and found that like the bigger the pipe is, the more likely it is to become turbulent. Or like this, the bigger the pipe, the smaller that critical velocity value needs to be for it to develop turbulence. And then the last thing he did is he vary the temperature of the water. So in general, warmer water is less viscous. So he found that like when you have warmer water, you also do not need as high of a velocity to get to turbulent behavior. So it was all those things put together. And then he also did a second part where he had like two flows going past each other and watched how that turbulence developed in between. In general, he found that like in that setup, you don't need the velocity to be as fast for turbulence to happen. That is the less quoted part of that paper. Yeah. And then there are these sketches of what he looks like in the back. All right. I'm going super fast. So an important thing to remember about turbulence, though, is that turbulence is not a function of the fluid. Any fluid can become turbulent. It is instead a combination of all three of these things. It has to be velocity, viscosity, and length scale. Together, that is, call that a flow, and turbulence is a property of this flow. So that right picture, that is the Great Boston Molasses Flood of 1919. I don't know if you guys know of this event. Basically a super big storage silo vat exploded because it was like a really hot day in January. And newspapers described it as like a torrential wave of molasses just crashing through the streets. It was the velocity got to about 35 miles per hour, which, right? Which is about the same as a tsunami when it is on land. And the wave was said 40 feet high, which, yeah, I don't imagine. But that teaches us to, one, corporate regulations, two, anything can be turbulent. And conversely, anything can be laminar. So this is a very small little algae in seawater. So this is just plain water. And because they are so small, that L is tiny. If you are a microbe swimming around in seawater, your life is laminar. Like, yeah. So that video earlier that Shashin showed of how you could like unstir something if the viscosity is big enough, that is kind of what their life is like. Just, yeah. We also have like pyroclastic flows, like when a volcano explodes, that lava that comes out is super viscous, but similarly, it's because of how fast it is going, it can exhibit turbulence like behaviors. Okay, makes sense? Great, awesome. Yeah. All right. So now how would we go about describing turbulent flow? Found this, yeah, I thought it was weird and funny. So yeah, so say we are presented with something like this. How would we go about even applying, say, B-Stokes, not B-Stokes equation to whatever the heck is going on here? Well, even though turbulence is not actually chaotic, it's not actually random, it's fully governed by the Navier-Stokes equations. We use the language of random variables and statistics to describe what's happening. So we treat it as a stochastic process and say if we have a time series of, I don't know, velocity, then each timestamp of that time series is a random variable. Then if we have a collection of random variables, we can do statistics on it and apply all of these moments. do we remember statistical moments, guys? What's the first moment? Yeah, exactly. So the first moment is the average. That is kind of the first thing that we do. And in general, the method is to separate the flow into the average and the fluctuating part. That is called Reynolds decomposition, and that is the next lecture, right? So I'm not going to go into the math of that, but I am going to draw what it kind of looks like. So if we have a general flow, say coming out of a pipe, and it's doing all sorts of things, we can decompose it into this mean behavior plus whatever's left over. And then we can do all sorts of other kinds of statistics on this, like find out its variance, the variance of the turbulent flow kind of shows us like how much kinetic energy is contained. So yeah, generally that is our approach. Questions, concerns? But then what exactly is this mean? In this case, it is very easy to see that like, yes, there is a mean value, there's a mean flow, and then all of these things are kind of fluctuations on top of it. What if the mean flow itself is changing over time? So this would be an example of a non-stationary process. The way I think about it is, let's go back to, if we go back to this flow, let's say this is coming from a reservoir and is slowly running out of water. Then this stream gets weaker and weaker and weaker and dies off. And that means that this shape, this mean flow shape, is changing over time. But how does that make sense? Because isn't a mean by definition steady over time? Well, not always, because you can instead have a running mean. So to describe non-stationary statistics, usually what you do is you take a running average filter and then you subtract that from your process. But then if I am doing a running average, that means I have to pick a window size. So by necessity, calling something stationary versus non-stationary means that you are choosing a time scale or a length scale. So this I'm saying is non-stationary, but what if this second time series is actually just a tiny little part of this first time series? Then in this sense, this flow is part of the turbulent field. But then if we really zoom in and say that it is stationary, then it is not part of the turbulent flow. So yeah, that is very common. Okay, that's kind of the end of my prepared material. Does anyone have any questions? So if you take complex systems here, sorry, I'll get to you in a bit. If you take complex systems here, this like transition of energy in between different length scales and different like orders of complexity, that is almost definitionally what nonlinear means. I think it's very interesting. Sorry, what is your question?
Can you say more about why the time series on the right does not represent a turbulent flow, but the time series on the left does?
I did not mean to say that. I am saying that the way we define what that turbulent flow is different for the time series on the right versus the time series on the left. Here we would be subtracting like a line or a diagonal line. Whereas there it would be a constant throughout the entire ensemble. But I guess the part that I probably maybe was confusing is I was saying that perhaps because we don't actually know what these time scales these are, it is possible that maybe this second time series is actually a zoomed in version of that first time series. So why is it that sometimes we say we have non-stationary statistics with a field that goes around the slope, but in another reference frame, I guess, we are saying that that is not turbulent, and that all of these wiggles, including the slope, is part of the turbulent. Yes, Andrea.
I was just gonna say, it's the whole all models are wrong, some are useful. Basically, it's pick a window that is useful for what you're trying to look at. So as Helen is saying, nothing exists that is fully stationary or non-stationary. It all depends how you zoom in onto it and how you look at it. But for example, if you're looking at a wave, you might want to average over a wave period. And that way you're looking at how things change. Your mean is your mean over a wave period, and your variance is your variance over a wave period. Obviously, your mean is going to change with time then if you're looking at your mean over many different wave periods, right? So it really just depends on the window size that you're choosing, and usually you try to choose something that makes sense for whatever problem you're trying to solve.
Yeah, very succinctly put, Andrea. All right, I guess we got to finish 10 minutes early then. Unless anyone has more questions.
You can start the next one early.
Do you want to just start talking about rentals? I mean, this is exactly where you start, right?
Yeah, 30-minute break, just start early.
Mm-hmm.
Start our big food. Yeah.
Great. Yeah. Have fun, guys.